We'll be starting out with the role of tolerances in 3-axis machining, basically how tolerances control, how we can use tolerances to control the quality of the machining process itself. And then we'll talk about some of the effects of steep and flat areas on toolpath behavior. There are certain things that you need to watch out for depending on the configuration of the part you're machining, the types of machining methods that you can employ. And you need to be aware of some of the behavior of the toolpaths. We'll also go over containment of the cutter, so to give you more effective containment, so you can machine specific regions or areas of your part. We'll also talk about advanced stock creation methods specific to 3-axis milling. And then a couple of interesting things we'll be talking about after that will be minimizing stair steps and horizontal roughing. Now, there's something new that we introduced last release, and it's a pretty powerful method. Also, we talk about optimized machining and horizontal finishing, which many of you might not be aware of. Also, we'll dwell upon pre-drill start points, how to use pre-drill start points for roughing. And then finally, we'll be talking about default parameters, how you can actually set up your own defaults using knowledge bases. And then finally, toolpath editor tools. Once the toolpath is generated, and if you need to make any last-minute edits, you can use some of the toolpath editor tools to actually fine-tune your toolpaths. So quite a few things to cover today. So Uday, go ahead, please.
Thank you, Joe. Hello, everyone. Good morning, good afternoon, or good evening to you all. And thank you again for joining us for our AMS webinar series for this month. Today, we will be covering power topics for 3-axis milling. And we will start by covering the very first topic here, which is going to be a role of tolerances. And to demonstrate this, I'm going to first go ahead and run through a few slides here, so you could see how tolerance affects your toolpath. So in this particular slide, as you can see, we have different tolerance settings of 0.1. It could be inches or millimeters depending on the units you're working in. So this one is generated based on inch units. You can see that the slacker, the tolerance, you'll see that the toolpath have much longer chord segments, which affects the result and the quality of the machine part. So the smaller the tolerance that you set, or the tighter the tolerance that you set, it'll reduce the chord segments, which improves the accuracy as you go smaller or tighter on the tolerance, which in turn results in more number of go-to motions, because the chord segments or distance between each point to point move of your toolpath is going to be much smaller. So depending on the the part that you're working on and the accuracy and the finish that you need, you may want to set those tolerances accordingly in your roughing and finishing process when you program your 3-axis operation. And in addition to setting up the tightening up the tolerances, you can also fit arcs to your toolpath. So fitting arcs to toolpath will basically convert the linear motions into arcs if those motions are in any of your principal planes, 3 principal planes, which could be your XY, XZ, or YZ. The example shown here shows arcs being fit in the XY plane. So if the toolpath points, the motions are form an arc and they're fitting an arc, the arcs will be automatically fit to your toolpaths when you select arc fitting. And I will be covering that in an example as we go along during the demonstration here. Now I do have another slide here which basically also shows you a side view or an end view of how the tolerance affects the accuracy here. As you can see, with the slacker tolerance, you can see the faceting in the toolpath, and also you'll notice that the chord segments are much larger. Tightening up the tolerance and fitting an arc, it results in a much smoother and much more accurate toolpath. So the dark blue toolpath motions that you see here are arcs being fitted to the toolpaths, and the turquoise or the cyan colored motion that you see here are your linear segments. And we will cover this as we go along in an example here during our webinar today. Okay, so I have a core of a a tray insert that is loaded in RhinoCam. And as you can tell here, I have a few operations programmed. So the first thing we're going to take a look at is the role of tolerances. So I have a horizontal roughing program. The part is in millimeter units. And as we take a look at this toolpath, you will notice the, with the effect of the tolerance, the chord segments are much longer or much larger, as you can see here, with the default tolerance of 0.25 millimeters that's been set for the in tol and the out tol in here, and the toolpath has been generated. So as we generate and simulate the toolpath, I'm going to run simulate to end, which is running through it, and you'll also notice the facets and the effect of the tolerance on the rough part in here. Now, as we go back and tighten up these tolerances, so I'm going to step through the levels before I tighten up the tolerance. So you can see for each of the levels, you'll see the chord segments are much farther apart based on the tolerance settings that we put in. If I go in and tighten up the tolerance to a value of 0.05 millimeter for our tolerances, and you will notice the tool paths are much more smoother, resulting in much smaller chord segments and improving your quality of finish on the resulting part as you take a look at each of these Z levels in the roughing operation. Now the same goes with other operation types as well, finishing as well. I'm just using the roughing operation as an illustration here for today's webinar, and I'm going to go ahead and run through the simulation for the roughing operation with a tighter tolerance. So you will now notice the difference between the roughing with the slacker versus tighter tolerance, as you can see in the result of the simulation. The one that you're noticing here with a slacker tolerance, and this one is with a much tighter tolerance. So, making the tolerance much smaller, tighter, will result in a higher accuracy finish, again, at the expense of more number of lines of code, and the computation time would also be longer for a tighter tolerance. Now, to fit arcs to your toolpaths, there's a couple of things you will need to do. One is you'd have to go into your CAM preferences and machining, and you would need to make sure output arcs as linear segments is not checked. And in your advanced cut parameters tab, you will need to set the arc fitting tolerance by selecting perform arc fitting, and you would specify the fitting tolerance to 2 times of the tolerance that you specify for your in-tol out-tol. So I have it set to 2 times, and then generating the toolpath will fit arcs to toolpaths wherever is feasible in the 3 principal planes. So in this particular operation we've generated, we have a horizontal roughing, which is also known as Z-level roughing or roughing in levels. So all of the toolpaths generated are in XY planes, parallel to the XY. You can see the arcs are being nicely fitted to the toolpath, and you can also set the maximum arc radius under CAM preferences and machining, depending on the max radius that your machine or controller is capable of handling. Now I do have another example in here where you can see the same effect of tolerances. One with the slacker tolerance, you can look at the chord segments are much longer. With the tighter tolerance, it's more accurate and much smoother, resulting in a much finer finish. Okay, so we will now move on to our next topic in here, which is going to be the effect of steep and flat areas on toolpath behavior. To demonstrate this, I'm going to be using the same model in here, and I have a parallel finishing operation program as part of the finishing or a pre-finishing process. And you will notice that depending on the angle of cut that you specified in your parallel finishing, so in this particular case, the angle of cut is set to 0 degrees, which means the cutter traverses back and forth parallel to the x-axis as the angle of cut is set to 0. And as you run into steep areas on the model, you'll see that this leaves like larger stair steps in here as the parallel finishing is riding up and down on these vertical walls. Now, as you go along these sides, you will notice that it results in a much smoother transition in the parallel finishing operation. So to eliminate these steep areas that you're noticing here in the scalloping that you're noticing in the toolpath, you will need to change the angle.
I just wanted to give an analogy of why we're seeing these little jerky motions when we're going along close to the edge of a vertical surface. You can think of it as if you're hiking along a mountain, a very steep mountain, for instance, and you're hiking on the sides of the mountain. Even a very small change in your, your step could result in a large vertical drop. So that's what's happening here. If you have a very steep surface and the tool is actually riding on the side of that steep surface, so even a very small change in the normal direction of the tool can cause a significant change in the vertical axis of the tool direction. So that's what you're seeing. So you got to be aware of that if you're cutting steep areas like this, and if you're going to go along that steep area like this toolpath is being illustrated here, you might see these jerky motions. So thanks, Uday.
Thank you. So going along, as you notice the steep, the riding up and down on the walls, but when you're going across, you get a much nicer transition. So to basically address the steep sections in here, you would have to, one of the ways you could do it is make a copy of the operation, and you can run it in the across direction by changing the angle of cut from 0 to 90, or if it was 90, you can change it to 0. So you can basically get a much cleaner finish on this side, but you'll notice now the effect of the going along the steeper section on this side. So you would have to basically program one with a 0 angle of cut and then one with a 90-degree angle of cut. Now you could contain them to specific regions by creating regions or selecting surfaces. We'll talk about that later, but I just wanted to kind of go over the effect of steep and flat areas toolpath behavior with parallel finishing on this particular example. Now I'm going to go ahead and give you an example of the effect of steep and flat areas on a part where we can use some horizontal finishing toolpaths, which is also, we call it a Z-level finishing. This particular part, you can see that the part is much more free form or sculpted, where we do not have a lot of steepness or variation on the part. Now, programming a part like this with horizontal finishing or Z-level finishing is not the most ideal way to do it, because horizontal, or it's known as Z-level, where it's ideally used for steep sections where you have, it's also known as like a waterline finish, where you want to step it down in constant Z levels. So in this particular case, since the part that we have over here is not too steep, programming a horizontal finishing or Z-level finishing will result in much more gaps, or you can see the toolpaths are much spread further apart, even though you have set a tighter step down distance in the cut levels tab.
Conversely, I would also add that the part that Uday showed previously would be better suited for horizontal finishing or Z-level finishing rather than parallel finishing. So again, it's all dependent on the part shape or the configuration of the surfaces. And so you got to be aware of this. Thank you.
Thank you. So the horizontal finishing has been generated on this particular part we looked at earlier, the core model, and you can see the horizontal finishing generated on the part which is near flat, or we could call it freeform or sculpted, since there aren't too many steep areas. So ideally, you would want to generate a parallel finishing toolpath or something similar on a part like this, as opposed to using a horizontal finishing toolpath.
So a good rule of thumb would be, if you have a part is generally flat like this, you would use parallel finishing. And if your part is steep, then you would use horizontal finishing. So that's a very good rule of thumb to follow.
Thank you. So the next topic we're going to be covering today is how to contain the cutter in different types of 3-axis toolpaths. And to illustrate this, I'm going to be starting with this particular example, which we just looked at. Now, to be able to finish this part, you will notice that we have a region selected for containment, which basically extends up to the part extents in here. As you can see, the part extents. We have selected a containment region so that the toolpath can be generated for the entire part. Now, as we select a containment region, the tool tip stays up to the region in here, as you can tell by looking at the toolpath and the toolpath display. The tool tip stays up to the region. So in this particular case, since we have a fillet or a radius surface towards the end of the part, you can tell that the cutter is not able to get all the way down fully on the side. So if I go into the toolpath viewer, you'll be able to see that the tool is not going all the way down on the side in here. So whether you're using a ball mill cutter, the tool, you can take a look in here and see that it's not going all the way down. So in order to be able to cut all the way down on the side, we need to make sure that the region that you're selecting is extended past the edge of the part by at least your cutter radius if you're using a region or a curved region as your containment. So one of the ways you could do it is you can offset the region in your CAD. In this case, it was Rhino. I can offset the region and pick a region that's offset by at least the cutter radius and generate the toolpath. So you will see that the tool goes all the way down, cuts past it in here, goes past completely on the side. Now, since I did not want the tool to go past on these sides, I did not extend the region over here. I just did a offset on one side, just along one of the directions. So on the y-axis here, the same goes over to the other side as well. Now I could apply the same to when you're using cutting across at 90 degrees. Now you'll notice that the cutter goes all the way down, but it creates these retracts to the clearance plane. Now you're noticing this effect because there is no underlying geometry or surface for the toolpath to project down to. So basically when it gets down on the side, it retracts up to the clearance plane before it does a transfer. Now there's a couple of ways how you can eliminate this. One of the ways is by inserting a plane. You can insert a planar surface, or it could be even a sculpted surface depending on the type of geometry you're working in. So you can insert a planar surface in this case, and generating or regenerating the toolpath will create a nice transition down to the floor of the surface that you created. And the toolpath stays contained to the curve that you've selected, which is the offset curve. Now you can alter this plane in here. You can select it, and if you want to move it up slightly, in this particular case, I've chosen the plane to be down by the cutter radius so that the side of the cutter can fully get down on the side. As you take a look at it over here, I'm going to switch the tool to a ball mill. I had it on a flat mill for some reason. So if you take a look at it here, it gives you enough room for the cutter to get down all the way down on the side to be able to cut it fully. So you want to make sure that you basically move the plane that is at least passed by the cutter radius if you're using a ball mill, so it basically clears all the way down to the edge. If you move the plane up in the Z, I'm going to turn off the snap and just lower it down slightly below the part, and then regenerating the toolpath will automatically stay up to the plane. The same thing goes whether you're cutting, the angle of cut is 0 or 90 degrees, you'll have the same effect. So to be able to cut down fully on the sides, you'd want to make sure that you offset it by the cutter radius. That would be the minimum distance that you want to offset it away from the edge by the cutter radius. This would be helpful in parallel finishing operations. It could be for any type of part that you're working with. This is just an example to illustrate that. I'm now going to be going over a few other cutter containment examples.
You said a couple of things to eliminate the retracts. The other easy one would be to use the skim.
Absolutely. So we'll generate this toolpath again. I apologize, I forgot, I missed it out. So in the clearance plane, we have a cut transfer method. We can set it to skim or clearance. The default choice is clearance. So you can change that to a skim and specify a small value. I can put in like 10,000, and that'll basically just retract 10,000 above, resulting in a skim transfer and not retracting all the way out to the clearance plane. So the same thing can also be set whether you're cutting along, 0 or across. So in this particular case, you wouldn't have much effect on the skim clearance because you're going parallel to the x-axis, which the angle of cut is set to 0. You'll see the effect more when you're cutting across as you're writing down the fillet or the radius in here. Okay, I'm going to go over to the next example in here, which we will be covering the effect of containing the cutter. So here I have a basically a half section of a guitar body, and these fillet sections here, these are steep sections, and I have used a method called between two curve machining to program this. Now this between two curve machining is part of our advanced 3-axis methods. It's available in our Pro and Premium configurations of our mill module. Now, the between two curve machining, the toolpath morphs or flows between the two curves, and the toolpath is being projected to the 3D model. In this particular case, I have selected two curves. One curve is on the edge where the fillet begins, and the other curve is where the fillet ends. Now, selecting these two curves and generating the toolpath will result in this toolpath. However, the cutter is not able to get all the way down on the side. So similar to what we did in the case of parallel finishing, we will need to create a curve that's offset away from this edge by at least a cutter radius, and then we will need to generate the toolpath. So generating the toolpath here, you will notice that the toolpath goes past the edge and cuts all the way down. However, the toolpath, it's riding up and down, and since there is no surface or geometry to project down to, so you're going to see this shakiness in the toolpath because you don't have any a surface geometry or part geometry underneath it. So again, creating or inserting a surface at the bottom. Now the surface could be planar, it could be sculpted, and generating the toolpath will eliminate this shakiness on the toolpath that you're noticing with the between two curve machining operation. So again, this plane that you create can be set wherever that's appropriate. If you only want to go halfway past the model, I can move the plane up in the Z axis and then regenerate this toolpath. So the toolpath will not cut beneath the plane. So the next example we're going to take a look at would be one with a horizontal finishing toolpath. A similar type of model. And again, we would like the cutter to go past this edge where the fillet ends. So you would want to make sure that you create a curve and you offset the curve away from the edge by your cutter radius. Now in this particular model, we would also want to make sure that the cutter stays away from this pocket region. So what we have done here is created a region, a closed curve region that stays away from the neck pocket of this guitar body, and generating your horizontal finishing toolpath by selecting that particular curve region not only cuts and finishes up the fillet radius all the way down to the bottom. We also have a Z containment specified in here in the cut levels, so not to cut below a certain Z depth. And it also stays away from the neck pocket. So you could create these curve regions to contain the cutter to specific areas when generating your 3-axis toolpaths. Now let's go ahead and take a look at another example in here. In this particular example, you can see that the part has vertical walls in most areas, except there's a draft in 2 of these sections in here. So we've selected the silhouette around the part as a containment region, as we have the stock defined as a rectangular piece of stock, a box stock. So to contain the cutter just to the part extents, I've chosen a containment region that represents just the extents, the silhouette extents around the part geometry. Doing so will result that the cutter is not able to get down all the way down on the sides. So if I go back and run a simulation, you'll see that the cutter is unable to go fully down all the way down to the bottom, and it leaves more material. Now again, to be able to effectively program this, you would need to create a region and offset it out in the areas where you need to cut all the way down to the floor. So I'm going to go back and reselect my containment region. So I have 2 regions, 2 rectangular regions here drawn, and then generating the toolpath will allow the cutter to go all the way down to the floor. So the roughing operation takes into account the stock that's being defined and looks at the part geometry where the material needs to be removed. Now, if you do not want the cutter to roll over around this edge, you could insert or create a simple surface like a wall in here, and then regenerating the toolpath will treat this also as part of your part surface and avoid that from the cutter from rolling over. Now the same technique can also be applied with the finishing. In this particular example, I have a horizontal finishing programmed, and as you can tell, the cutter is not able to get all the way down to the bottom on this drafted wall or the taper wall in these 2 sections. So we will go ahead and modify and reselect the region, the one that we've offset in here, pick these 2 and generate the toolpath. So this allows the cutter to cut all the way down on the side.
I think the main takeaway out of this region and containment section that Uday just went over is that you can get quite creative with creating geometry and using that in the machining for containment. Not only regions, not only curves, what we call regions, but also surfaces, containment surfaces like the plane that he created. You're not necessarily restricted to planes. You could do sculpted surfaces as well. So you can be quite creative based on the type of parts that you're machining. I think that would be the biggest takeaway from this section. Thanks, Uday.
Thank you. Also, we could select part surfaces as control geometry. In this particular example, I'm going to go with a 3-axis radial machining toolpath. We can pick part surfaces, and then you can actually select 1 or more surfaces. And as you specify a tool, and generate the toolpath based on what you set for the surface extent condition. You can basically have the toolpath either stay onto the surface, or you want to have it go past, or keep it to the surface. So you have three different controls here. Surface extent on, basically the tooltip stays up to the edge of the surface. Selecting past will go past by the cutter radius and automatically checks for the adjacent surfaces in here. So it automatically gauge checks for adjacent surfaces. So you can do surface selections, not just curve regions. You can also pick surfaces as part surfaces as your regions for containment. And you can choose a surface extent condition to past, on, or to, depending on what you're looking to accomplish. Okay, so we'll be moving on to our next topic. This would be advanced stock creation methods. And there are several different ways we could create stock geometries. With our Pro and Premium configurations, we have 3 additional stock types. We have a part offset stock, extrude stock, and stock from selection. So we'll be covering these 3. We've already covered the other stock types in our earlier webinars. So today we'll be focusing on part offset stock. Now the part offset stock is useful when you're working off of your casting. So if your initial stock that you're going to be starting out is going to be a casting that you're going to be working out of, so rather than having to create a box stock and then rough it out, you would want to basically, your casting would typically be like an offset of your finished part itself. So you can specify a radial offset distance in the part offset stock, and then picking OK will create a stock that's a true 3D offset of your actual part geometry itself. Now, this particular part is in millimeter units, so I put in a radial offset distance of 0.5 millimeter. I'm going to display the stock visibility in here. And then if you go over to the Simulate tab, you will notice that the part offset stock is generated. Now, when I go ahead and create a roughing toolpath, the part offset stock that you created is what is taken into account for generating the toolpath. So you're minimizing any unnecessary cuts or cutting in air, and make it much more effective for your finishing process. Now the part offset stock is available in Pro and Premium configurations of our mill module. The next stock type we will be covering here today will be stock from selection and stock from extrusion. I'll be covering those two here in just a moment by using another example. So in this particular part, what I have here is a core model, and you could be working with stock materials where you may have, if you're working with like materials like MDF or foam, you may have materials that could be stacked up to form the actual shape of your part. So you could actually model those in your CAD. Here in this case, it could be modeled in Rhino. So basically I have a stack of material stacked up in here where there's just features that needs to be machined. So you could be saving your raw material, the stock material that you're going to be using for milling as well. So you could define your own stock or model your own stock, and then you could place it on a layer in your CAD. In this case, I've created a layer called stock, and I've placed this solid model on a new layer. And I could highlight or select this object in here, the geometry, and then go into stock and select stock from selection. So defining it as stock from selection will create a stock from the selections that you made. Now, this feature, stock from selection, is available in Pro and Premium configurations of our mill module. A few things that I would like to mention here is the geometry that you're selecting has to be watertight, which means there aren't any open edges. It needs to be a closed poly surface or a closed mesh. We could select either closed meshes or closed poly surfaces as geometry for defining stock from selection. Now, once you have defined the stock is now displayed in RhinoCam. The next step you'd want to do is make sure you hide this solid model, or if it's on a different layer, you can turn off the layer visibility. So when you turn off the layer visibility, you're actually viewing the part And as you select setup and highlight stock visibility, you can see both your stock that's defined and the part. So before you create a roughing operation, you would want to make sure that you toggle off the visibility of the actual solid or the mesh geometry that you use for defining your stock. And then generating your toolpath will compute the toolpath based on the stock that you created. So you're not cutting air, you're saving a lot of time and material. So when I run a simulation here, the toolpath is generated based on the stock that you've defined, which is the stock from selection here. So when you're working with large scale models, and if you have stock that's made up, like built up with different shapes, you can model those stock shapes in your CAD and then generate the toolpaths by defining stock from selection. So there's a roughing process generated using stock from selection. Now the next type of stock geometry I would like to cover here is stock from extrusion, or also known as region stock. So let me go ahead and delete the stock in here. So stock from extrusion or region stock can be created by selecting planar curves. So you can have one or more curves created. You need to make sure that the curves are closed, and you can select these curves. I can hold shift or control to multiple select. If you're working in Visual CAD CAM, you can use the control key. In Rhino, you can use shift, or you can window select them and then go up to stock and use extrude stock. So the stock is basically an extrusion of the curve geometry that you selected. You could specify a high and a low Z. Automatically, it'll determine the high and the low Z based on the part. In this particular case, I can set the low Z to be 0. Pick OK. So the extrude stock or the region stock is created. Now this extrude stock or region stock feature is available in Pro and Premium configurations of our mill module. So generating the toolpath will compute the toolpath based off the stock geometry that's been defined. So you can see that there aren't any toolpaths generated outside of the stock extents. Again, another way of defining stock for your roughing process. Now you could also have a nested region for stock. So for example, if I need to draw a geometry, so I can go ahead and say I want to put a hole in here. And I can move this up to the same plane where this geometry is located. I could select these two curves and define stock from extrusion. So basically a stock that you define can also have a hole or a bore on it. So extrude stock, you could select multiple curve geometries to define your extrude stock. So we're now going to move over to the next topic, which is going to be minimize stair steps in horizontal roughing operation. To cover this, I'm going to go ahead and switch back to our original example we started out with today. This would be the tray core model. So we have generated a roughing operation already, and we looked at the simulation of this earlier during our webinar. And you'll notice that with the roughing operation we've created, it creates stair steps like the Z-level roughing. You can see these large step downs for each cut level. Now, one of the ways you could do it is minimize these stair steps in horizontal roughing. This is a new feature available in our latest release. And as you go into the roughing operation and go over to the cut levels tab, you will notice that the minimize stair step option is available under cut levels. Again, this feature is available in Pro and Premium configurations, minimize stair steps, and you can specify the intermediate step down distance. So setting it up to 25% will be 25% of the step down distance. And generating the toolpath will generate the roughing toolpath in Z levels, and then it goes back and cleans up the stair steps, similar to how a re-roughing operation is done. So as you take a look at the simulation here, you'll see that it does the first level and then works its way up to go back and clean up to minimize those stair steps. So there's a simulation with minimized stair steps and comparing it without minimized stair steps. So this would be an efficient way to bring the stock as close as possible to the net shape of the finished part in your roughing process, so it makes it easier on the tools for your pre-finishing and finishing process. So again, this minimize stair step option is available in the cut levels tab and is included in Pro and Premium configurations of our mill module. Okay, so we're now going to move over to our next topic, which is basically optimized machining in horizontal finishing. Most of us have used horizontal finishing for finishing steep areas or Z-level finishing. Now, if you have parts that also have flat sections or flat areas that you'd like to finish along with the steep sections, you could go into the horizontal finishing operation and select optimized XY machining. So selecting this and generating your horizontal finishing toolpath will also generate toolpaths for the flats that you have and results in an offset cut pattern. As you can see, the optimized machining is generated on these flat sections on the top of the core as well as on the floor. I'm going to go ahead and bring in another example where you can see in a cavity the same thing, how it works inside a cavity as well. So I have the cavity for the same tray part, and there's the horizontal finishing with optimized and comparing it without optimized. So the optimized machining can be used for machining flat areas as you're stepping down in levels, generating your Z-level finishing toolpath. So being able to finish both steep and flats, you could use horizontal finishing with the optimized XY machining.
So there was a question on the minimized stair step roughing. Can't you do that same thing with a smaller DZ or a delta Z for each cut level? And maybe you can explain what's the difference between using very small cut levels to get that same effect as opposed to using minimized stair steps.
Sure, we'll certainly do. Thank you. So if you take a look at these two operations, I'm going to go over the information. So you'll notice that the horizontal roughing with the current step down results in about 7,300 plus go-to motions. And if we go ahead and program the horizontal roughing with a much smaller step down, you're basically roughing it down for the entire area of the stock and the part with a much smaller step down, which is resulting in going to be exponentially much longer toolpath generation times. And you don't have to, for example, if I set this to 10% tool diameter for the step down, for each of the levels, you're basically roughing out the entire part at a much smaller step down, so which basically adds more to your machining time. So it's probably much more efficient to use a larger cutter to clear most of the materials out and then work your way self up as you want to just clean up the area. So here I've used a much tighter or smaller step down in here for each of the levels. This adds much longer toolpath generation, toolpath machining time for the toolpath, versus using the minimized stair steps where you're generating it with initially much larger step downs, and then you're working yourself up to clean up just those sections around the model, like it does like a re-roughing operation in between those stair steps.
So if I may add to that, what's happening in minimized stair step roughing is when you're taking the maximum possible depth of cut with your cutter first. So you're removing a bunch of stock with your maximum possible step down. that your cutter can allow. And then we are using that in-process stock. So you've already cleared out a lot of material. And now we're using that in-process stock to only go in and whittle away the amount of material you haven't removed in the preceding Z levels. So it is quite different from using a much smaller delta Z and machining the entire stock model. Because if you're doing that, you're actually cutting the entire stock model for each delta Z. So that's a significant increase in the number of toolpath points. That's what Uday is pointing out.
So I'm comparing the two roughing operations here, and you'll notice that we are at 7,000. If I use a delta Z of 10%, you're almost looking at 7 times, or just under 7 times, yeah, which also exponentially increases your machining time. So the minimized stair steps is the way to go to reduce the delta Z between each stair step so as it does a re-roughing operation. Okay, so we'll move over to the next topic, which is how to use pre-drill points in 3-axis operations. So in this particular example, I'm going to be talking about a roughing operation. So considering that we have this cavity that we need to mill, we would like to probably pre-drill a hole so that would make it easier for the roughing process. So I'm going to be inserting a hole machining and drilling operation to start with. I'll pick a drill point in here, or I could pick a circle. So in this particular example, I'm going to be using a drill point. We'll use a tool for the process, and then we'll specify a drill depth and then generate the toolpath. So I'm drilling down 40 millimeter deep with a end mill, or it could be with a drill bit. So once we've done the drilling process, we would like the cutter to engage in or enter in at this pre-drill location at the start of the roughing operation. So if you generate a horizontal roughing operation, the roughing toolpath automatically figures out the best possible location for the entry or your ramp motion. However, if you wanted to use the location of the pre-drilled hole, you'd want to go ahead and edit the roughing operation and then go to the Start Points tab under Control Geometry, click on Select Start Point, and you can pick the start point or the point that you used for your pre-drill operation. Now generating the toolpath will plunge or will create the ramp motion at the point where you chose for your pre-drill location. So it's automatically going to move your entry to the location where this pre-drill point is. So that gives you the control to basically specify where you wanted the cutter to enter in on the roughing. Now this can also be done for both roughing and re-roughing operations, picking the start point. So the cutter ramps in at the pre-drill location for each of the cut levels. Okay, so we're now going to go ahead and cover how to set default parameters once the simulation is completed here. As you can see, it's each cut level, it's using the same start point for drilling. Okay. All right, so let's move over to the next topic here in today's webinar, is setting default parameters using knowledge bases. Now, a lot of the times as we program our machining operations, we would like to use a certain set of parameters. So when we go up to the machining methods, in this case 3-axis, if I choose horizontal roughing, I would like to use certain set of parameters. So for example, for the clearance plane, I may want to use stock max plus a distance of, let's say, 5 millimeters. I would prefer to use a skim clearance at all times. I'll specify a skim height. And cutting parameters, like I could set my tolerances to be a certain setting at all times and the stock to leave. So each of these parameters that you're inputting, you're basically repeating this over and over again for each and every time you're trying to generate any operation. All of the mop parameters that you're specifying in here have to be keyed in or inputted each time. So as you go through the process of entering, so this repetitive work can be eliminated by defining or setting up defaults. To set a default, once you have a machining operation created, you could right click on the operation, and then from the menu that shows up here, you can choose Save as Defaults. As you click Save as Defaults, you'll be prompted with the Save as dialog, and it automatically points you to the defaults folder, default directory in here, and I can give it a name. For example, I can call it default knowledge base 1, and I pick Save. So now the mop parameters for the horizontal roughing operation that we just inputted is now saved to the default knowledge base. So the next time I go ahead and program a roughing operation, whether it's the same part or a different part, I go up to 3-axis and roughing, you will notice that the parameters that you saved in defaults are automatically loaded. So you don't have to go through the process of re-entering each and every parameter. So your default settings are being saved in here. And you can have multiple defaults. We will talk about that in just a moment. But before I do that, I would like to talk about how we can add defaults for different operation types. So you can have a default for each mop saved in the same knowledge base. Now going to this parallel finishing operation, I may want to use a certain settings each time. So for example, I would want to tighten up my tolerances, reduce my step over, leave my angle of cut, change it to 90 degrees. And then I can also still do the arc fitting in here in the advanced cut parameters, and then generate this path. Now once the operation parameters, you've set the operation parameters and generated it or saved it, you can right click and choose Save as Defaults, and it automatically updates the defaults knowledge base file for the parallel finishing operation. So when I go into creating a new parallel finishing operation from the menu, you will see that it automatically loads the parameters from your defaults that you just set. Now I could do the same thing for horizontal finishing. Right click, Save as Defaults. So all the parameters we set now are saved in the defaults file. Now if I go ahead and pick a different file in here, so I'm going to go back and choose a different example. I'll go pick one moment here. Okay, so I'm going to go ahead and pick a different part, and you'll notice that the part is in millimeter units. If I go ahead and select 3-axis horizontal roughing, you'll see that the parameters are being loaded from your defaults, whatever you set. So this basically eliminates the need for you to having to go back and re-enter the parameters that you'd like to use, over and over again. And you can have the defaults set for each and every operation type in here. If you go back to an operation that you already saved into the defaults and right click and say Save as Defaults, it's going to update the defaults with the new settings. So you can have a default for each operation type. You can have it for roughing, parallel finishing, horizontal finishing, 2-axis profiling, pocketing. For each and every operation type, you can have the default set and saved. Now this default is actually being saved and automatically loaded in your app data folder. And as you go into the CAM preferences and machining, you will notice that the last default knowledge base you chose is automatically set to be loaded at the start. Now, if you want to revert it back to the system defaults, you can always select the pull down menu and change this to undefined. This will basically set it back to the factory settings or the system default settings. So you can switch this back from the one that you chose to undefined and pick OK. So now it reverts back to the system default settings, as you can see right here. Now, if I want to create a second defaults for a different type of either material you're cutting or type of process you're using, you can set it to undefined, make your changes to the parameters in here so you can apply these changes, and then right click and choose Save as Defaults, and you can give it a new name. I can say Default Knowledge Base 2, or you can name it based on the material you're cutting. So we now have 2 defaults knowledge base is set, and the last saved default settings is what gets loaded here, and you can choose which default knowledge base that you'd like to use before you start creating your toolpaths. I could pick from knowledge base 1 or 2. So if I go back to knowledge base 1, as I create new operations, it's going to load the settings from the default knowledge base.
And the way you can organize defaults, you can get actually quite creative also with that. We've seen users use organized default parameters based on tool size. So maybe you're interested in setting particular default parameters when you choose a particular tool. And so you could save the knowledge bases or default knowledge bases based on the tool size. Or as they mentioned, you can save it based on the material you're machining, or even the kind of parts you're machining. Maybe you're getting guitar body parts and you wanted to have defaults for guitar body parts, and then maybe ukulele body parts or something else. So there's quite different ways you can organize defaults and use it. So it's your creativity is the only limitation there, we feel. Thank you.
Thank you. Also, to mention that if you're working in inch or metric units, you may want to make sure you have separate default files saved, because these are default knowledge bases, so you don't want to mix and match them. So you can have one for, set of, inch or English parts that you're working in, and one for metric or millimeter parts that you're programming. So you can have two different default knowledge bases, and you can choose them which default knowledge base to use before you start programming it by just going to CAM preference and machining. Okay, the last topic for today we have is basically toolpath editor tools, and I'll try to cover this toolpath editor tools in here. Now, this is a very useful tool that's available in our Pro and Premium configurations of our mill module. The toolpath editor tools can be accessed by going into the toolpath object from any one of our machining operations. So I can double click on a toolpath and access the toolpath editor. And there's two tabs in the toolpath editor, which is called global edits and selection edits. Now these tabs will appear if you have Pro or Premium configurations of our mill module. Now, one of the many advantages of this toolpath editor tools are, for example, in the case where you had machining, and for some reason you had a the tool broke, or you had a small gouge or something, and you want to basically cut slightly underneath, or offset the toolpath down in the Z to go back and refinish it without having to modify your part or modify your go back and regenerate the toolpath. One of the tools you could use under global edits is called transform toolpath. So you can basically move the toolpath in the Z, so you can basically lower it down by a few thousand. So for example, it's like similar to how you transform your CAD geometry. Instead of transforming the geometry, you're actually transforming the toolpath itself. So I could say I wanted to basically move it down by 10 thousandths, or in this case, I'm working on a millimeter part. I'll just put in 0.1 millimeter. So I'm lowering it down in the Z and then picking OK. Will actually take your toolpath and lower it down by the distance that you put in here. So if you want to go back and refinish it, so it basically, if you had a gouge or something that you notice on the part and you want to basically take care of that, you can just basically offset it down in the Z-axis. So it'll basically move the entire toolpath down by the distance. Now there's also other tools where you can transform toolpaths, where you can rotate, mirror, and scale. In this particular example, we talked about how we can move the toolpath. So you can basically go to transform, set the move, and you can specify a distance in here, and then you pick OK. That basically moves the toolpath, and you can see that the toolpath is now moved by 1/4 of a millimeter. Now, one of the other ways how you can use your toolpath editor tools is when you make a change, it automatically flags the machining operation folder dirty, and tells you that you made some edits to the toolpath, so you can go ahead and post this out directly without having to regenerate it. So if you regenerate it, it's going to undo the toolpath edits that you just did. So regenerating will basically revert it back to what you had before you made those edits in the toolpath editor. Now let's say you had a part that requires a very long job run. It could probably run over several hours or has to run overnight, and you may want to stop it and then go back the next day and then continue from where you left off. So rather than having to go back and reprogram and regenerate the toolpath for those sections, you can use the toolpath editor and go into the selection edits tab, and you can basically select a section of the toolpath and delete it. So for example, I can choose select cuts by picking a drag rectangle, and I can drag a window. In this case, I'm looking it down from the top view, and I can select a section in here, drag a window. You can see those toolpath motions are highlighted, and I can cut to eliminate those sections. I'm basically trimming those toolpath sections out, and then basically you can post it and then resume cutting the next day. Or if you had a tool breakage and you want to basically go back and just continue from where you left off, you can use these toolpath editor edits to perform these tasks, so you can continue from where you left off. You could also create a region for containment. So rather than picking just a drag rectangle, you could be even using a containment region in here. In this case, I'm going to just basically draw a rounded rectangle, and I can use select inside a closed curve. I can pick the closed curve, so it automatically picks all of the toolpaths inside that section, and then I can choose cut to delete those sections, or I can even do isolate. Basically, it does an inverse of cut. So these tools, the part of toolpath editor tools, are available in Pro and Premium configurations of our mill module. I apologize, I ran a little over time today, but I would like to conclude my part of the demonstration and hand this back over to Joe.
Thank you, Uday. There was a couple of questions I want to quickly answer before we shut down. How do you do the Z-level display of the toolpath? There's a button in the toolbar at the bottom. Do you want to show that, Uday?
Sure, absolutely. So as you select a roughing operation, so now the Z-level display works in most of the 2.5 axis methods and 3 axis methods like horizontal roughing and horizontal finishing. Now the Z-level display would not be applicable if you're just doing a parallel finishing without step down. So if you have a roughing operation or a horizontal finishing operation, the first step is to select the operation. Step 2 is make sure your toolpath visibility is toggled on. And once you have the toolpath visibility toggled on, you can select display toolpath in levels, and selecting this will display the dialog, Z-level display dialog, and you can step through the Z-level display.